So now let's take a look at the specific method that's based on regression. Now this is one of the many different methods. In fact, it's one of the simplest methods, and I choose this to explain the idea because it's simple. So in this approach, we simply assume that the relevance of a document with respect to a query is related to a linear combination of all the features. Here I used xi to denote the feature. So xi of q and d is a feature. And we can have as many features as we would like. And we assume that these features can be combined in a linear manner. Right? And each feature is controlled by a parameter here. And this beta is a parameter. That's a weighting parameter. A larger value would mean the feature would have a higher weight and it would contribute more to the scoring function. The specific form of the function actually also involves a transformation of the probability of relevance. So this is the probability of relevance. Right? We know that the probability of relevance is within the range from 0 to 1. And we could have just assumed that the scoring function is related to this linear combination. Right? So we can do a linear regression. But then the value of this linear combination could easily go beyond 1. So this transformation here would map the 0 to 1 range to the whole range of real values. You can verify it by yourself. So this allows us then to connect the probability of relevance, which is between 0 and 1, to a linear combination of arbitrary features. And if we rewrite this into a probability function, we would get the next one. So on this side, on this equation, then we'll have the probability of relevance. And on the right-hand side, we will have this form. Now, this form is clearly non-negative, and it still involves the linear combination of features. And it's also clear that if this value is actually negative of the linear combination in the equation above. If this value here, and if this value is large, then it would mean this value is small, and therefore this whole probability would be large, and that's what we expect. Basically, it would mean if this combination gives us a high value, then the document is more likely relevant. So this is our hypothesis. Again, this is not necessarily the best hypothesis, but this is a simple way to connect these features with the probability of relevance. So now we have this combination function. The next task is to see how to estimate the parameters so that the function can actually be applied. Right? Without knowing the beta values, it's harder to apply this function. Right? So let's see how we can estimate beta values. Right? Let's take a look at a simple example. Right? In this example, we have 3 features. One is BM25 score of the document and the query. One is the page rank score of the document, which might or might not depend on the query. We might have a topic-sensitive page rank that would depend on the query. Otherwise, the general page rank doesn't really depend on the query. And then we have BM25 score on the anchor text of the document. Now, these are then the feature values for a particular document or query pair. And in this case, the document is D1, and the judgment says that it's relevant. Here's another training instance with these feature values. But in this case, it's non-relevant. Okay, this is an overly simplified case where we just have 2 instances, but it's sufficient to illustrate the point. So what we can do is to use the maximum likelihood estimator to actually estimate the parameters. Basically, we're going to predict the relevance status of the document based on the feature values. That is, given that we observe these feature values here, can we predict the relevance here? And of course, the prediction will be using this function that you see here. And we hypothesize that the probability of relevance is related to features in this way. So we're going to see for what values of beta we can predict the relevance well. What do we mean? Well, what do we mean by predicting the relevance well? Well, we just mean in the first case for D1, this expression here, right here, should give high values. In fact, we hope this to give a value close to 1. Why? Because this is a relevant document. On the other hand, in the second case, for D2, we hope this value will be small, right? Why? It's because it's a non-relevant document. So now let's see how this can be mathematically expressed. And this is similar to expressing the probability of a document. Only that we are not talking about the probability of words, but talking about the probability of relevance, 1 or 0. So what's the probability of this document being relevant if it has these feature values? Well, this is just this expression, right? We just need to plug in the xi's. So that's what we will get. It's exactly like what we have seen above, only that we replace these xi's with now specific values, right? So for example, this 0.7 goes to here, and this 0.11 goes to here, and these are different feature values, and we combine them in this particular way. The beta values are still unknown, but this gives us the probability that this document is relevant if we assume such a model. Okay, and we want to maximize this probability since this is a relevant document. What do we do for the second document? Well, we want to compute the probability that the prediction is non-relevant. So this would mean we have to compute 1 minus, right, this expression. Since this expression is actually the probability of relevance, so to compute the non-relevance from relevance, we just do 1 minus the probability of relevance. Okay, so this whole expression then just is our probability of predicting these two relevance values. One is 1 here, one is 0, and this whole equation is our probability of observing a 1 here and observing a 0 here. Of course, this probability depends on the beta values, right? So then our goal is to adjust the beta values to make this whole thing reach its maximum, make it as large as possible. So that means we're going to compute this. The beta is just the parameter values that would maximize this whole likelihood expression. And what it means is, if look at the function, is we're going to choose betas to make this as large as possible and make this also as large as possible, which is equivalent to say make this the part as small as possible. And this is precisely what we want. So once we do the training, now we will know the beta values. So then this function would be well defined. Once beta values are known, both this and this will be completely specified. So for any new query and new documents, we can simply compute the features for that pair, and then we just use this formula to generate the ranking score. And this scoring function can be used to rank documents for a particular query. So that's the basic idea of learning to rank.